Okay, so let's take a look at geometric sequences. We've spent some time looking at arithmetic sequencing. We touched on geometric sequences. We know that arithmetic sequences are ones where we are adding a constant each time. So a geometric sequence is probably what you would guess is that you are multiplying by a constant term each time, and that is a geometric sequence. So for example, we can see there that they've given us 3, 6, 12, 24, and of course that would be times 2 times 2 times 2, and so 2 is our constant that we're multiplying by. And most of you guys can probably identify, I hope all of you can identify that just by looking at it, but in some cases there are some numbers that might not be as obvious, in which case what we can do is we can divide each term by its previous term. So no different than in arithmetic sequences, you would find your common difference by doing t2 minus t1. So in arithmetic, we know that d is equal to t2 minus t1 because we're going to be adding that constant or that common difference. So for geometric, we call it a common ratio, and that is r, and we find that by dividing t2 divided by t1, or of course t3 divided by t4, and that would give us your constant ratio. So we know for the example above, we've already stated that the constant is 2. So the common ratio is Tn being any term and Tn minus 1 being the term before it. So I'm totally fine, obviously, if you just use T2 divided by T1, and that would be fine. So that is our common ratio. I'll just highlight this. So let's take a look at class example number 1, and it says explain why each of the geometric sequences is geometric. So what we're looking for is that common ratio. So in some cases, again, you guys can probably identify it just by looking. If we wanted to prove it, then what are we looking for is that T2 divided by T1 is the same as T3 divided by T2, or 12 divided by 6 is the same as 24 divided by 12, and so all told for this first one, we know that r is equal to 2. And you guys could probably have told me that without doing all of the work before. For the second one, so take a moment, hit pause, and see if you can figure out the ones for B and C. Okay, so we can see that in B, the common ratio is -5. One thing to remember is it is negative. Why? One thing we're seeing here is we have a negative term 1, positive term 2, negative term 3, positive term 4. So because it's flipping back and forth, positive, negative, we know that the common ratio has to be a negative. When the common ratio stays the same, then the signs will stay the same. So in this case, we're seeing -10, -5, -5 halves, -5 quarters. Because the numbers are getting smaller each time, then we recognize that the common ratio also has to be a value less than 1. In this case, we're looking at 1/2. -5 halves divided by -5 is probably not the easiest thing to figure out for some of you guys, but you could also test it then. If we know that -5 divided by -10 is 1/2 or 0.5, then what's -5 times 1/2? Of course, it's -5 halves, and then again times 1/2 is -5 quarters. Okay, so take a look at class example number 2, and they're just simply asking you, is it arithmetic or geometric? So does it have a common difference or a common ratio? And if it does, then state what that is, and then continue the sequence to figure out the 5th and the 6th term for each. So again, hit pause and complete those 3, and you can hit play again once you're ready. Okay, so just take a look at your answers. So for A, we should have geometric with a common ratio of 3. because 24 divided by 8 is 3, T2 divided by T1, and so to find term 5, we're multiplying by the common ratio, so 216 times 3 is 648, times 3 again is 1,944. For part B, it is arithmetic. It's going down by a constant, and that constant common difference is negative 36. So we've got our term 5 and term 6 is negative 36 and negative 72. For C, it is geometric, and we can find the ratio again by dividing term 2 by term 3, and we can confirm it's negative, positive, so the ratio must be negative, and it is negative 2/3. Term 5 and term 6 we find by multiplying by the common ratio, so term 5 is negative 16/27, and term 6 is positive 32/81. Taking a look at the next page. Skipped a few. Okay, so basically the little investigation, and they tell the story in the paragraph there, indicating that they're measuring moss. That sounds exciting. So on the very first day, the mass of the moss is 8 grams, and then it's 12 grams the next day, and then 18, and then 27, and they tell you that it forms a geometric sequence. So the common ratio is we're dividing term 2 by term 1, and so common ratio is 12 divided by 8, which is 3/2, or I'm also okay with 1.5 because it is a terminating decimal, and so R is 1.5. And so if A is a first term and R is a common ratio, then complete the table. So the first term is 8, the second term is 8 times 1.5. The third term is, again, we're multiplying by R, in which case every time R is 1.5. And so you can see it's kind of the same thing. Instead of adding plus D, so plus 1D, plus 2D, plus 3D, where times R again. And what do we have when we multiply by the same number, the same value, is you're building something that is exponential. So times R is 8 times 1.5 is the same as A times R. 8 times 1.5 times 1.5 is A times R, or A times R squared. And then term 4 is 8 times 1.5 times 1.5 times 1.5, which is, of course, 27, as they've shown us. And so that term 4 would be AR cubed. When we continue, then term 5, of course, is AR to the 4th, and Tn. Well, how does our n value compare to that exponent? Well, the exponent is always 1 less than our n value. So we're looking at AR to the exponent of n minus 1. So in this particular case, for this specific geometric sequence, so for any geometric sequence, it would be Tn is equal to AR to the n minus 1. For this specific one, though, what would we be looking at? Well, what is our A value? It is 8. What is our R value? It is 1.5, and to the exponent n minus 1. You might be tempted to multiply 8 times 1.5, but you're not going to do that. And why? Because we're recognizing that order of operations comes into play, and we have to do the exponent on the base 1.5 before we multiply. So do not multiply 8 times 1.5. This is as simplified as it will get. Okay, so let's take a look then. So here they go through the formula for the general term of a geometric sequence. So depending on whether you're using A for term 1 or, of course, T1 for term 1. So take a look at that. Let's take a look at class example number 3. So it says determine the formula for the general term, and hence, that means then, calculate the indicated term for each of the following. So remembering that we're looking at the formula for your geometric sequence as Tn is equal to a times r to the n minus 1. So in this case, what do we know is a is 5, and r, 15 divided by 5 is the same as 45 divided by 15, which is our r value, which is 3. We are just doing a general term, so n stays as n. So our general term then is going to be Tn is equal to 5 times 3 all to the n minus 1. And again, do not multiply a and r. Order of operations says you have to figure out that exponent first. So when we're trying to figure out term 9, we can substitute in. Now n is equal to 9. So then that is 5 times 3 to the 9 minus 1, or 3 to the 8th. So we're looking at whatever 5 times 3 to the 8th. So we want to figure out what 3 to the 8th is, but you should be able to enter that into your calculator, right? So if you're entering into your calculator, you can enter it in exactly as is, remembering that you're using the hat symbol, so it looks something like 5. You could use the brackets if you want, or you can use the times symbol, 3 hat 8, and that should give you your answer of well, if I had that. Let's go back. And so 5 times 3 hat 8. And whoops, I do not want that. Oops. Go. So 5 times 3 hat 8, and that is 32,805. Okay, let's take a look at the second one. Again, looking at that general term. So we're looking at A. Our first term is 1/3. R, sometimes it's easier to just look at, okay, what am I multiplying by? Because it gets to negative, positive, negative, I know it's going to be negative. It switches back to positive. 1/3 times what? Will give you negative 1/6. 1 times 1, and 3 times 2. So negative 1/2 is our R value. So then our general term for this specific geometric sequence then is Tn is equal to 1/3. That's our A value. R value is negative 1/2. And that is all to the n minus 1. If I'm looking for term 7, then it is 1/3 times negative 1/2. So this is term 7, and that is all to the 7 minus 1, or to the 6. And so I don't want to, well, I can use my calculator, certainly. Be very careful about how you enter that in, but I'm probably not going to do it as a decimal, because I know it's going to be a repeating decimal with that 3 there. So I know that 2 to the 5th is 2 to the 5th is 32, so 2 to the 6th is 64. Because there's going to be 6 negatives, then that ends up being positive, so it will be 1/64. And so 1/3 times 1/64 then is 1/192. Excellent. Okay, so let's take a look at class example 4. Then Janice and Gary trying to determine the number of terms in this sequence. So using the general term formula, write and simplify an equation. So what do we know again? We know that A is 32. We can see here, how are we getting to each one? So R is equal to 2, or we could divide 64 divided by 32 and check that with the next one. And what do we know in this case? We know our Tn value is 16,384. So we can say Tn is equal to A times R to the n minus 1, or 16,384 is equal to 32 times 2 to the n minus 1. And if I want to simplify that equation to figure out what n is, I want to isolate, so I will divide both sides by 32. So divide this by 32. So I'm going to divide that also by 32, in which case we end up with, I believe it's 512 is equal to 2 to the n minus 1. So that is a simplified equation that we now need to solve. So we actually haven't seen anything like this just yet, any equations to solve quite like this. So Janice is using guess and check to write each side of the equation with a common base. And so if we are Janice, we're probably going through our powers of 2. So again, starting with some things that we know, we had just looked at the fact that 2 to the 6 is 64. Believe it or not, not that far off. 2 to the 7th is 128. 2 to the 8th then is 256. So then that tells us that 512 is 2 to the 9th. So because 512 is 2 to the 9th, then we can substitute that in. So rather than writing 512 as 2 to the n minus 1, then 2 to the 9th is equal to 2 to the n minus 1. So because the bases are exactly the same, then the exponents must be the same. So 9 must equal n minus 1. So from there, very quickly, we should be able to say then, adding 1 to each side, that n is 10. Okay. Gary instead is using his graphing calculator. A great use for his graphing calculator. Anytime you're trying to solve an equation with your graphing calculator, the easiest thing to do is essentially to set one side to y1. So y1 will equal the left side, which is 512, and y2 will equal the right side, which is 2 to the n minus 1. So put that into your calculators, and I'll just hit pause right now, or you hit pause right now while you put that into your calculators, and we'll come back and show how we can solve that with the calculator. Okay. So let's take a look then. So you've entered into the calculator, and you can see right here we've got y1 is 512, y2 is 2, and we use that hat button above the division symbol to indicate we're going to the exponent, and we don't have an n, so we just use that variable button, and you can see there is an n there. It enters in an x. That's totally fine, and it's 2 to the x minus 1. What's going to happen then is if we hit graph, and you can see right here on my graph picture that it says that there's going to be an error. And part of the reason for that is that it exceeds what my graph can do. So what we need to do is we need to set our window. So if we take a look, if I was to go into the graph, it's not really graphing a whole lot for me right here because that's a lot of information. It's trying to process that. Oh, it came up with a little something there. But right now, our standard window setting, remember, goes from positive 10 on the x to negative 10, positive 10 on the y to negative 10. What we want, though, is we want y equal to 512. We're nowhere close. We're only at 10. So that means that we need this y to be a whole lot higher. So we need to adjust that as well. We kind of sneakily already went by Janice's method, and we know that x is equal to 10. Right now, at this point, we can see when n is equal to 1, then we could figure out what the corresponding y value, same thing. When it is 2, that would be your corresponding y value, and so on. And so let's take a look then. So we go back to window, and at this point you can see the y max is 10, so we want that to be significantly higher. So, whoops, jump that. So y max, I need it to be at least 512. So let's make that 600. The y scale, I really don't want my calculator to count up by ones in this case. So in this, perhaps instead, I'll have it count up to 50 or by 50s. And because I know that the intersection, you can see my graph already adjusting for us. It's right on the edge of the screen. So I'm going to make that a little higher, and let's make that 15 then. And if we hit graph at this point, then there's that y equals 512, so that is clearly on the screen. It's nice, I can see where each of the increments are. Remember, I've asked it to count up by 50s, and there's that intersection. So what do we want to know at this point? Where does y1, so where does 512 intersect with 2x plus 1, or 2 to the n minus 1, and that intersection point is the value of x where those two are equal. So to find that, we are going to go to second trace or calculate, and we want the intersection, which is the fifth one. So you can arrow down to the fifth one, or you can just hit 5, enter, and it says the first curve. Where do we want our cursor? We just want our cursor pretty close to that intersection point. So we'll just go from left to use our right and left buttons, bring that closer, hit enter, and it says take a guess. Is that the closest point that we want? Yep, and there it is. So it says when the x value is 10, then the y value is 512. Excellent. So let's go back, and so what we're going to do is, and you don't need to write this down, or maybe you don't need to write it on a test, but certainly right now perhaps you might want to make note of it. So you're doing second, and it's calc, and you're going to calculate the fifth option, which is the intersect. And the solution, therefore, is 10 is your x and 512 is your y. But remember, rather than it being your x-axis, it's actually your n-axis. So in this particular case, that is what tells us that n equals 10. Excellent. So let's leave it here then at this point, and please check ManageBac for your assigned questions.